When a physical object like a metal cantilever beam bends under a load, our goal is to calculate exactly how it reacts to that force. For simple one-dimensional objects like a straight beam, we historically calculate stiffness using standard continuous calculus. This traditional analytical approach yields a clean algebraic equation that we easily solve on paper. But this is what the actual computational finite element method code looks like for that exact same beam. Right here is the programmatic stiffness matrix calculation. It requires defining specific integration points, calculating physical coordinate mappings, and cycling through iterative array multiplications inside nested loops. Using this massive algorithmic architecture to solve a simple one-dimensional beam is mathematically unnecessary. It is completely overkill. The technique driving this code is a numerical integration method known as Gauss quadrature. Gauss quadrature is a procedure that abandons the continuous curves of standard calculus, substituting them with discrete arithmetic evaluation at highly specific points. Why do computational engineers purposefully discard a perfectly accurate, simple calculus equation in favor of complex, discrete approximations? To answer that, we have to look at the three things Gauss quadrature demands: highly precise locations, highly specific weights, and repetitive calculation loops. We need to deconstruct this code, moving chronologically step by step through its core loop. We use this specific method because mapping out the chronological loop for a one-dimensional beam is the exact mathematical prerequisite for modeling more complex reality. The algorithmic breakdown begins with a single step, identifying the mathematical domain of our structural element. Above our physical beam element sits the mathematical domain, spanning from negative to +1. The code translates these abstract bounds directly onto the beam's length, mapping 8 distinct integration nodes. Each physical coordinate is half the length multiplied by the Gauss location, +1. With our coordinates mapped, we introduce the specific matrix required to calculate bending stiffness, the shape function's second derivative, which we'll call hxx. This derivative matrix dictates mathematically how the structural beam bends at any given point along its length. We programmatically evaluate the hxx matrix at one of our newly mapped physical coordinates. This generates a four-dimensional row vector specific to that exact node. Instead of evaluating a continuous curve, we now possess discrete numerical data firmly locked to a single localized point on the beam. This evaluation is only the initial setup. The code stages this process to execute for all the designated integration points. While the specific code block integrates across 8 points to demonstrate the loop, 3 points would technically be sufficient to accurately evaluate a simple beam. The immediate problem is determining how to transform these individual, discrete vectors into a cohesive, usable stiffness matrix. By mapping discrete points and evaluating their derivatives individually, we successfully translate continuous physical space into a programmatic array ready for processing. We now enter the core for loop of the finite element code, where the actual computational heavy lifting occurs. First, our hxx row vector multiplies by its transposed column vector, creating a 4x4 matrix. This is scaled by a Gauss weight constant based on location. The algorithm loops, repeating this exact multiplication and weighting for all points, adding them into a running sum. Once the loop completes its final iteration, the raw numerical integration sequence is technically finished. However, we must apply one final required scaling factor mandated by numerical integration rules, the Jacobian. For our one-dimensional problem, the Jacobian acts as a simple constant multiplier equal to exactly half the total length of the physical element. At this point, the integration block is finished, but we do not yet have a complete physical stiffness matrix. To bridge math to reality, we multiply the matrix by real-world material constants, the aluminum's modulus of elasticity, and the beam's second moment of area. Finally, we apply a specific transformation matrix evaluated at the exact endpoints of the element to format the final structural equation. The dense array of algorithmic instructions is now fully assembled and ready to be processed by the software solver. This specific sequential arrangement of multiplying, weighting, and iteratively summing provides the numerical framework required to evaluate complex element matrices. The solver executes the code, feeding the assembled stiffness matrix into the final calculation to determine structural deflection. The algorithmic loop calculates a maximum deflection of exactly 1.0. That 1.0 metric matches the exact theoretical answer derived from standard closed-form calculus perfectly. We just executed a massive architecture of nested loops and numerical arrays to arrive at a value we could have found with basic algebra on a single sheet of paper. The value of this approach lies in the modular architecture we just constructed, mapping the domain, evaluating the matrix, looping the nodes, and scaling the result. This visually expands into a broader architecture, modeling two-dimensional surfaces like structural plates. We take our one-dimensional code and wrap a second for loop around it to iteratively integrate across a new y-axis. Standard calculus struggles to cleanly resolve these complex two-dimensional interactions, but our discrete loop handles the expanded array seamlessly. We push this logic to its limit, modeling acoustic waves interacting inside a solid three-dimensional cube. By adding a third nested for loop to account for the z-axis, we instantly upgrade our basic script into a robust three-dimensional computational engine. As we scale upward across dimensions, the only significant modifications required in the code are updating the internal shape functions and adjusting the Jacobian scaling factor. The core loop remains the same. The Gauss quadrature procedure creates the multi-dimensional architecture necessary for the finite element method to handle real-world geometry.